we found that the magnetic field at a point on the axial line of a circular loop carrying current is given by V equal to mu 0 by 4 pi into 2 pi I a square divided by a square plus x square all raised to 3 by 2, where x is the axial distance from the center of the loop and a the radius of the loop. Now here we have to consider two special cases. First special case is that suppose the point lies at its center. So when the point lies at its center, what we can consider here as x equal to 0, being at the center, because x is measured from the center. So when I put x equal to 0 into this particular equation, I get the field at the center will be equal to, when I put x equal to 0, this will be 0, a square only coming here, a square all raised to 3 by 2, a square all raised to 3 by 2 will be equal to a cube, and therefore we get this a square, a cube, and there is a square coming, and finally we get the field equation is mu 0 by 4 pi into 2 pi I divided by a. This is the field at the center, and this we have derived earlier. So we can get the result from the same result from this equation. Now, second special case is that suppose the point falls far away from the center of the loop. I mean far away from the center, not infinity. There is no meaning in saying that at infinity the field is 0 only. Okay? So, if the point lies far away from the loop, from the center of the loop, what it means is that x is very, very large compared to a. This is what we put into this one. Means x being very far away. That is far away point means x is very large. So x is coming along with this a here. Therefore, we can compare x with a so that x is very large compared to a. So when I put this condition into this, effectively a square becomes negligible compared to x. Therefore, this becomes x square all raised to 3 by 2 becomes x cube, and therefore B, far away point, will be equal to mu 0 by 4 pi into 2 pi I a square divided by x cube it becomes. Then there is a doubt possible always. Here I consider x negligible, so why can't we neglect from here? See, we are comparing a with x. So x alone we cannot consider, a alone we cannot consider, a compared to x only it becomes negligible. So here we can compare because they are coming together. So compared to x is negligible. So in the denominator a can be neglected compared to x, but here there is no x coming. So that a square remains as it is, and therefore the equation becomes like this. Okay. Now from this equation we will move on to another particular formula, 2 pi I a square. This one together, when I take 2 pi a square into y, I can write it like this. So from this one, if I can write like this, then this will be the area. That is pi a square is the area of the circular loop and I is the current flowing. Therefore, I can rewrite this as 2 into capital M. I am representing this particular quantity as capital M, and that capital M we call it as magnetic dipole moment. So, as we are getting a quantity magnetic dipole moment from the derivation, that means that a circular loop carrying current is acting as a magnetic dipole with its one phase acting as north pole and the other phase acting as south pole. This is another point to be noted. Understood? Therefore, I can rewrite this equation as mu 0 by 4 pi into 2m by x cube. So this is another result we are getting. Keep in mind this one. Okay? So, far away point and at the center. And we understood that circular loop carrying current is acting as a magnetic dipole with one phase acting as north pole and the other phase acting as south pole. These are the results coming from the equation. Now, for those who are going for higher levels of discussions, let us see, a question will be always possible with comparing the equation these two. That is at the center and far away point. Or at the center and this one particularly. Sometimes. Then, how to treat that one? That is it. So these are the special cases. Now I am going to the problem solving side. Let's see. So we got B at the center is this one, and this is the B at distance x. Now, how to relate these two? Let us see. If I take a quantity here, that is at the center, it is what? 2 pi I by A. So I take the denominator A, and here also I take E. Means I am multiplying and dividing this equation with A. Then mu 0 by 4 pi into 2 pi I, right, divided by A, this one. Mu 0 by 4 pi into 2 pi I by A. That will be now equal to B at the center, or let me write it for you, that mu 0 by 4 pi into 2 pi I by A, and what remains? A cube divided by A square plus x square 4 raised to 3 by 2. And therefore, B on the axis, this is that axis field, will be equal to, this is B at the center into a distance function, a cube divided by A square plus x square all raised to 3 by 2. Now this equation you can use for comparing the field at the center and field on the axis. Clear? Okay. Now, as we said that the loop is acting as a magnetic dipole with its one phase acting as north pole and the other phase acting as south pole. How to identify that? Let us see. Suppose I have a circular loop carrying current like this. And suppose the current is flowing clockwise. As I look from here, the current is flowing clockwise. So when it is flowing clockwise, I will be holding the hand like this to find the direction of the field around it. Means it goes like this. So when in the frame, from all sides, the field is going into. So here the magnetic field is going into the plane. Okay. And when I take the other case, that is, suppose the loop is here and that loop is carrying current in the anti-clockwise direction like this. So I will be holding the thumb like this and the field goes like this, and inside the loop from all sides the field is coming towards you. Sorry, this is into the plane and this is towards you. This is into the plane. Okay, fine. Now this is the case with what? Coming out when it is anti-clockwise, and here it is going into the loop when it is clockwise. Now, when we compare this with the magnetic dipole, magnet, bar magnet, that bar magnet, when we consider this is north pole and this is south pole, and we find that the field lines are coming out from the north and field lines are going into the south from outside. Coming out and going into the south. So going into, that means that this acts as what? The south pole, and coming out, this will be acting as the north pole. So this will be the south pole and this will be the north pole of the circular loop carrying current. So these are the results we are supposed to identify. Okay? Very important for solving problems. Alright?